And we call them colligative properties. So we're going to talk about how when you dissolve something in something else, how the solution is going to have different properties from what it was before you dissolved something in it.
Can I ask an actual related question real quick?
Sure.
Why is it that when you put milk in tomato soup and then you heat it up, it comes out?
I've never put milk in tomato soup.
How do you make it?
Why do you put milk in tomato soup?
To cool it
I
down?
don't
is
know,
that-
that's my mom. No, because you have to put, it's like condensed and then you have to put water in it, but my mom puts in milk. And then it like creeps
And
out.
then you warm it up at what?
It like kind of separates.
I have no idea.
Polar or non-polar?
But that's a great question. I don't really know what tomato soup chemically looks like. I mean, I assume it's
Oh, there you go.
mostly water, but I don't, yeah.
Well, if you buy it in the can, you put
Ew.
stuff in the can,
That's
and then
disgusting.
you
Yeah,
fill it up
water.
with water and add more water.
Or
Yeah.
milk.
Or milk, yeah. I don't think,
I don't know.
I don't eat it.
Good question, but sorry I can't answer it. Okay, colligative properties. Okay? So, what this is again, this particular section, we're going to focus on the different properties between if I had a beaker with just H2O, pure H2O, or if I created a solution where H2O was the solvent, but I dissolved the solute in it. So let's say I have H2O and I dissolved in NaCl. Okay? You would expect the solution versus the pure solvent to have different properties, yes? They're not going to act the same exact way. And that's what this particular section is going to be focusing on. Okay? And the thing that it says, okay, the things that affect what a pure guy is going to act like versus the solution does not depend on what the solute is, but it only depends on the amount of solute you dissolve. Kind of interesting. Okay? It doesn't depend on how big it is, how small it is, if it's covalent, if it's ionic. The only thing that matters is how many particles you are dissolving. Okay? Now, we have to make one really important distinction that you probably have heard me say and probably know, but just a quick refresher. Covalent things, when they dissolve, do they break apart? No, they don't. Ionic things, when they dissolve, do they break apart? Yes. So let's say I have sugar versus salt. Okay? This will not break apart. It stays as one whole molecule. This will break apart into 2 particles. So this is going to have more of an effect on the solution's properties than this will. Okay? That's what this is saying. Doesn't matter what the substance is, we're really focusing on how many particles it breaks up into because you have to surround each of those individual particles. Okay? So here are, so there are 4 properties that we're going to talk about. Vapor pressure, boiling point, freezing point, and I might just vaguely touch on osmotic pressure. I talk much more about that in advanced chem. Okay? First, we probably need a slight refresher on what vapor pressure is. Yes?
No. We did it last chapter.
We did do it last chapter, but remember, okay? If I have pure H2O here, at a given temperature, we can have a certain amount of evaporation that occurs, right? We talked about that last chapter. Do you remember that? Okay? Well, when it starts to evaporate, what you create is this, remember, this theoretical bubble. Okay? Because you have atmospheric pressure holding the gas from escaping. It can't escape because the atmosphere is applying pressure, keeping it from escaping. So you create this theoretical evaporation bubble, right? Okay? And we said that as evaporation goes up, or as the temperature goes up, the vapor pressure does what? Goes up, right? More evaporation means more vapor to apply a what? Pressure. Does that make sense? So I would also then say a decrease in temperature lowers the vapor pressure, yeah? Yeah or yeah?
Yeah.
Okay.
Oh, that's so cool.
Now, let's say I got pure, which means only H2O, and I have dissolved NaCl. NaCl is what's known as a non-volatile solute. What do you think I mean when I say non-volatile solute?
It's not gonna explode.
Okay.
It's
Make a guess.
Not gonna react.
No. Doesn't easily evaporate. Okay? Salt. Okay, it's in solid form. Does salt easily turn to a gas?
Is there any solute that when it is over could
Yeah.
like evaporate more?
No. But I'm not gonna get too crazy. That's a much more of an advanced chemistry type topic. But you could have, like if you had alcohol and water, they're both volatile. Okay? So figuring out the vapor pressure would be based upon how much of each you have and what their pure volatility would be just by themselves. But yeah, that's a more down the line, deeper topic. What I want to focus on today and in this high school level chemistry is dealing with non-volatile solutes, or things that aren't going to contribute to the vapor pressure. Does that make sense when I say it's non-volatile, it's not going to evaporate, so if it doesn't evaporate, it will not contribute to the vapor pressure? That should make sense.
We'll bring it down.
Okay, let's talk. Let's say I have equal volumes of this, right? Equal volumes. Pure on this one side, solution on the other side, where I have essentially, what I've done is replace some of the water molecules with what?
Non-volatile.
A non-volatile substance. So per unit volume, which one's going to have more vapor pressure?
Pure H2O.
The pure H2O, because all of it can evaporate a little bit, right? But can all of this evaporate?
No.
No, there's some stuff in here that isn't going to contribute to the vapor pressure, and so anytime you add a non-volatile solute, it does what to the vapor pressure? Makes it go down, and that's why we call it vapor pressure depression.
Is that why it's not constantly
I'm
raining
in
on the
favor.
earth?
Constantly what?
Raining on the earth? Because the ocean is salt water. If it was pure H2O, it would probably rain more.
Yeah. I never thought about
That's
that.
so neat.
I wonder.
How does Gabe do all this stuff?
I've been thinking about that ever since you said that.
I mean, there's a lot of reasons why it's. Yeah. Wow. Huh. God, isn't God just a genius?
God is so cool.
God's a genius. So creative. It's pretty smart. Okay. So this is just kind of what I was talking about. The solute. I wouldn't say it interferes. I would change that to. It just, the solute doesn't evaporate, so you're basically you have less water molecules or less solvent that can evaporate, and that's why you have a lower vapor pressure. But it interferes isn't too bad of a word.
Discourages.
Discourages, okay, yeah, that'll work. Okay? So you have less water molecules that can evaporate, and so therefore less evaporation, less vapor pressure. Yeah? Questions on this before we move on? So the question is, let's see if you guys can figure this out. I just gave you this example, right? Let's say I have the same concentrations of both of these. Is one going to cause a greater vapor, will they have the same vapor pressure depression, or will one lower the vapor pressure more?
NaCl's gonna lower them
Why?
because it breaks apart.
It'll break apart into more particles. This will actually break apart into 5 molar Na and 5 molar Cl. that's a good segue into something that's really important. Let's say I've got something like this, and I say that this is a 2 molar salt, ionic compound, a salt. You guys know that a salt is just a fancy way of saying ionic compound?
Yes.
If I said that?
Yeah, a salt.
Not a salt, a salt. Okay.
Oh, fancy icon. Ionic compound.
Okay, how many particles do I have here?
Three.
Wait, 2, 1.
It's 1 particle,
Oh.
right? It's all together, right? 1 particle.
Yeah, yeah.
It's a big particle, bigger than the
But
products.
when it breaks up,
But
it's
when it
gonna
breaks
be-
up, I actually have how many particles over here? 3,
Wait.
Oh,
Yeah, 2 CL.
right? The chlorines aren't bonded to each other.
Oh.
Okay, this would be bonded to each other. This is not. That's 2 separate ions. That's an awful 2, but okay. So the point I'm trying to make here is if I have 2 molar of this, because of the 1-to-1 ratio, I really have 2 molar of that and 4 molar of this. Because this breaks up into twice as many particles as I had here.
Okay.
1-to-2 ratio. This is the same amount of particles as this, so they have the same concentration. That's going to be important for later, so I just wanted to kind of quickly show you that. You have a question?
How do you know this is going to break up?
Ionic will always break up, covalent will not. Metal, non-metal, 2 non-metals.
Well, why?
Why? Because water is really polar, and ionic has a strong polar charge, and typically covalent aren't very polar. Now, there are covalent things that do break up. Acids are one of them, but that's for a later time. Okay. All right. So,
Oh, yeah, that makes sense.
I'm going to show you, again, if you didn't think chemistry kind of like builds, wasn't there a relationship between vapor pressure and boiling?
Yeah.
What was the relationship that vapor pressure had to something boiling?
Once the vapor pressure equals
the pressure.
pressure.
Applied
Yeah.
pressure.
Okay, so we have H2O, pure H2O. We got this theoretical vapor pressure bubble. We got atmospheric pressure pushing down. Let's say the atmospheric pressure is this.
Oh.
What does the vapor pressure have to be for boiling to occur?
762.
Right? That would have to be 760 torr for boiling to occur, correct?
Yep.
So if adding a solute to this takes this and does what to it?
Makes it
Lowers it. Wouldn't it take longer for it to reach the atmospheric pressure and therefore boil at a higher temperature?
No.
Did I go too fast with that?
No.
Did you guys catch that?
Got
Say it one more time.
I'll say it one more time. Okay? First off, you should remember, okay, boiling occurs when the vapor pressure is equal to the atmospheric pressure holding it in. Remember that from last chapter, everyone?
Yep.
Okay? We just stated a second ago that when I add a solute, a non-volatile solute, and create a solution, what does that do to the vapor pressure?
It goes down.
It makes the vapor pressure go down. If the vapor pressure goes down, it's going to take a higher temperature or more energy to get it to equal the atmospheric pressure, therefore having a higher boiling point. So a solution will always have a higher boiling point or an elevated boiling point than a pure solvent would. The solid interferes with boiling, so the temperature has to be raised so that the vapor pressure can get to the atmospheric pressure because it was lowered due to adding that solute. All right, some math here. All right, so this is called the boiling point elevation equation. I want to make this very clear that change in TB, this is your elevation. It's not your boiling point.
So add that on to
So if I have pure water, what temperature does pure water boil at?
760.
100
Well,
degrees.
Temperature.
whatever. Oh.
100 degrees Celsius, right? That's when water boils. Okay? If I make it a solution, it's going to boil at a higher temperature. So let's say I do the math and I figure out that the change in TB was 0.15 degrees Celsius. What would be the boiling point of that solution?
100.50.
Everybody catch that?
Oh, what does the KB stand for?
I'll get to that in a second. Okay, I'm just saying that this is the elevated temperature, or how much it got raised. It's not the actual boiling point of the solution. So you have to, so for example, water normally boils at 100 degrees. If I add a solute and it elevates 0.15, what is the solution's boiling point? That makes sense, everybody? Now this is an experimentally determined constant, and this is what it is for water, right here. Okay, most of the time we're just going to be dealing with water. If they give you something that's different than water, they'll have to give you a different KB. Okay?
Wait, just KB, not the N.
Just the KB. What do you think that is?
The molality.
Molality. Little m. Who would have thought we would come back to that?
Not me. That's the bait.
Okay, so this is the elevation of the boiling point, not the actual boiling point. This is a concept that they'll give you or you'll have, and m is the molality. So let's do a problem here.
Okay. Well, first I have to find the mole. Unless that I gave it to you.
Okay, we got 20 minutes. We're cooking. Good job, guys.
Yeah, let's
What
call
about
it.
it?
Word cookout. Or not.
No one knows what brevin is?
It's not here.
Thanks. Okay, that helps. All right. Now, in a second, I'm going to talk about something that I alluded to a little bit earlier called particle molality. But before I do that, I'm just going to start with the simple one, which is a covalent guy. And we know covalent what?
Never splits.
Never breaks apart. That's important to remember.
Never.
Or
I should say never, usually, okay. A lot of times, again, instead of talking about all the nitty-gritty exceptions at this level, I just give you a blanket, this is always true, even though it's not always true. I do, kind of. Not on purpose, not, it's, you guys understand. It's so that I don't overbog you with a whole bunch of, I'd rather give you the typical, the usual, then bog you down with all the exceptions, and then once you know the usual, then throw a couple exceptions at you. Okay? So, it wants to know what is the boiling point elevation, so what are we actually just solving for?
The elevation. Oh, T.
We're just solving for this. That's all it wants, the boiling point elevation. It didn't say what is the boiling point of this solution. That would be different. Okay? We have 0.50 moles of my solute. It's added to 1.0 kilograms of acetone. So if this is added to this, what does that tell you about this? That this is that. No.
Oh, you're finding the molality through that you divide by.
Everybody see why that is the solute and this is the solvent? Because this is being dissolved in that or added to it. Okay? Now, notice that it told us the solvent was not water, so what did it give us? A different KB than the one you saw earlier that was for water.
Times.
Okay? So,
So the answer is 0.855.
we know KB. I'm just going to plug that in right now. 1.71 degrees Celsius over molality. What didn't they give us directly? Molality. But did they give us enough information to find the molality?
Yeah, 0.5 divided by 1.
First of all, molality is what?
The solute over solvent.
Moles
kg.
solute over kilograms of.
Okay, it's becoming apparent that we don't know this yet.
I know.
Yes.
Yes. I didn't give us. I will not give you this. I will give you the equations, but I will not give you solvent. Yeah, solvent.
Well, the sodium's on top.
Right? Now, thankfully, they could have given us grams here, couldn't they have?
They could have, but that would be a
They could have given us in grams as well and made us convert to kilograms. Is that possible that they could possibly do to you
Yeah, but they're
guys?
trying to be nice and
Yeah,
use this less.
but they don't want to. They want to be nice, but they also want to find the fine line between being nice and being able to educate and make students think.
Wow. That was
So since they gave it to me in moles and in kilograms, I can just plug them in and divide. 0.5 divided by 1 is?
0.5. Wow.
And the M's cancel.
M's cancel, giving you degrees Celsius. What is your elevation?
0.85 or 0.9.
Sig figs.
1.
3 and 3.
1. Shoot, you're right.
Okay. So this would be our answer for this particular problem. But let me just throw you something else that they could say. They could say the boiling point of acetone is 47 degrees Celsius.
Backdoor.
Okay, the boiling point of acetone is 47 degrees Celsius. What is the boiling point of this solution?
No, 47.85.
47.855. This is the boiling point if it's pure. This is how much it got elevated. So the solution's boiling point would be 47.855. I'm just showing you that is a way that they could come at you. Questions before I move on to the next problem? There wasn't a whole bunch of unit conversions here. Just be aware it's possible they could make you do some unit conversion. All right, particle molality. Important, and I kind of alluded to this a little bit earlier. And this is only important when you are dealing with ionic. Because ionic does what?
Breaks apart.
Breaks apart, okay? So what this is found by taking the molality of your substance to begin with and multiplying by the number of pieces it breaks up into. So if I have AlCl3 and I have a 2 molal substance of that, okay, this is going to break up into how many particles? It's going to break up into 4 particles, which means that the particle molality, or the total number of pieces you have in solution, would be 2 times
6.
4.
Wait. Oh boy.
2 times 4, so it would be
I thought the
8.
AL would have 2M and the 3CL would have 6M.
Which is what 2 times 4 gives you.
Okay.
First of all, you said 6, not 8.
You right.
Yeah. Okay?
You have 8 what?
So, if this, let's just say this, instead of saying molality, it said 2 moles. I have 2 moles of everything. When this breaks up, how many moles of aluminum would that be? 2. And if I had 2 moles of this whole thing, when it broke up, how many moles of chlorine would I have? 6. So remember, colligative property says how many pieces do I have, or how many particles do I have, not how big the particles are.
You have 8 whatever.
Well, particles.
Yeah.
That's what a mole is, right?
Oh.
Oh. Oh.
Mole's a number.
I don't want to slam my head in the door after that comment.
You've slammed your head on the whiteboard so many times.
I know, it's caused some mental. So that's just showing you that you got 4 particles, and this is why you would take your 4 and you multiply it by your initial molality. Okay, when do you do this? Ionic. Okay. So let's do an ionic guy. Of course they would do it this way. Look at what they gave us. Ah.
Gotta convert it to
Alright.
moles.
How do we end it on the same?
Okay?
No.
First of all, hot water, so water's our solvent. What was the solvent KB?
Water.
What was it?
Hot water.
0.512.
Yeah. Degrees Celsius per. Wait,
Okay.
wait, is that degrees Celsius per mole?
Slash molality. So that molality cancels and gives you degrees Celsius for your elevation temperature. Excuse me. So then we need to find molality. Okay, so let's find the molality of the whole thing stuck together first. Okay? First of all, this is my solvent, this is my solute. This is my solvent. Can I quickly change that to what it needs to be? What does it need to be in? Kilograms.
So you move it
Solvent needs to be in kilograms, so I'm going to quickly do that.
to 0.675.
And then this needs to be in
Mole.
moles.
So molar mass.
So I have to do the molar mass of this guy. So I'll just do it on the side here.
So kilo is 10 to the negative third, right? Third. 10 to the third.
Uh-huh.
That's what.
What's 4.4?
But you're dividing by it,
Yeah,
so
okay.
so you could say multiplying by 10 to the negative third.
Okay.
Okay? Anybody figure out the molar mass of this guy yet? So magnesium plus 2 times chlorine.
It's 95.21, but the molar is 4.46. Yeah, my phone.
96.21? I have 95. Did I write that wrong? Did anybody else get 96.21? You guys are waiting on me, huh?
I got 95. It's
95.21?
95.
4.46 is how many moles?
Oh, there, I got 95.
4.46. Is that what you said? What am I going to do with that then?
Put it
in
on the
here.
top. You're
I
welcome.
know.
Because this will give me my molality. Right?
Right.
You with me? Am I going too fast?
No, you're good.
Sorry.
Stop, guys. Anybody get it?
Yeah.
6.61. Now, this is the molality of it together.
Oh.
So what do we have to do with this number?
Put it into the equation.
Not yet.
But separate.
6 point.
This is what? What's this?
Ionic.
It's ionic, which means it's going to do what?
Break apart.
Break apart. How many pieces will it break up into? 3. So I got to take this number and
Divide by 3.
Times 3.
Wait.
Divided by 3.
Why do you multiply by 3?
I'm not going to divide by 3 because this is one piece. It breaks up into 3 pieces, so
Oh,
it's going
God.
to give me way more pieces when it's dissolved than when it's not
Oh,
dissolved.
And we said to multiply the last thing we just did.
So 19.
So it's 19.8 is what I put in here
times
to get my elevation.
2.
Oh, notice what they asked for.
Boiling point.
What is the boiling point? They didn't say what is the
100
elevation.
plus Whatever.
100 plus whatever you
Plus
get.
10.15.
So the elevation is 10.1-ish.
10.2.
Is it?
10, yeah, 10.5.
That's what it is elevated, but what is the actual boiling point of the solution?
110.
110.2, because the original boiling point of water, pure water, is what?
100 degrees
100 is when water will boil without adding a solute. When you add this solute with this much, it's going to elevate it quite a bit. 10 degrees.
Wow. Is that normal? Like,
I mean, that's a lot. This is a really
Okay.
concentrated guy.
Is it like honey or what?
Well, as you can see.
Sorry, questions? I don't want to go too fast here.
What? I feel
What-
like
what?
I'm not gonna be able to do this. by
What's your
myself.
question?
Where did you get the 10? I was trying to write things down.
Where did I get what, 10? This 10?
Yeah, no, wait, what?
That's a very satisfying
No,
thought.
like, you added 100.
Because 100 is.
So water regular boiling point is 100. And if I put this salt in water, it elevates it 10.2. So the actual boiling point of the solution would be the original boiling point of the pure water plus the elevation. So 100 to 10.2. That make sense?
Yeah.
Right? Because remember, when you add a solute, it raises the boiling point. So the solution will always have a higher boiling point than the pure guy, every single time. Shoot. I'm gonna skip this one.
Oh no,
What?
I'm doing it. I want to see if I can do it.
This one is tricky though. I should probably not skip it. This is the backdoor one.
Juice.
What did they give us?
They gave us
The change in temperature.
the increase.
They gave us the elevation.
Yeah. If we gotta solve for molality using the constant, so we just take that and divide it by 0.5.
Okay. In water, so we know our constant.
0.512.
All I do.
0.512 degrees Celsius over molality.
Okay, so I can solve then for little m, correct, using this.
Yes.
So 0.4 divided by 0.512.
Cancels out your Celsius.
Your Celsius cancels out, then it's 1 over 1 over m, which is the same as saying m.
That's gonna equal 0.78.
Okay, now, just take a little swerve here.
Which is popular.
It's my mom.
Here's a little swerve. This is the molality after this has broken up.
Oh my soul.
I want the molality of it combined.
Divided by 2.
So in this situation, you divide by 2. But
Why is it long?
I don't know. This isn't my final answer, so usually I overround until my final answer. Did everybody understand why in this situation I'm dividing by 2, but in the last situation I multiplied by that particle molality?
Because you're breaking.
I'm going the backdoor way. In the first situation, I needed to break it apart. In this situation, this is the broken apart number, and I want to combine it to get the concentration of that. It's a lot, isn't it?
Wait, how did you know that was?
What? Because I was going reverse. When I go forward, I break it apart to find the boiling point elevation. When I go backwards, the number I put in is the broken apart number, and if I want the molality of the combined, I'm going to divide by it instead. So if you want to say, you could write down when you're breaking apart, you multiply. What are you doing?
I was gonna take a picture of it.
When you're combining, you divide.
Please do not.
The good thing is, I know that you're probably thinking, well, how are we going to get through the last part of this? Well, the math is exactly the same. And I will show you here in a sec. Okay? So what adding a solute does is it actually decreases the vapor pressure. I'm going to give you the most common example that you probably have seen about adding a solution causes it to lower the vapor, or not vapor, lower the freezing point. What do people do? What do they do?
Antifreeze.
When they're, well, that's one way. What do people do when they have icy sidewalks?
They
Put
put
salt
salt
on
on it.
And what do you think that's creating?
Water.
It's creating it's a solution. It's creating a
So
solution
why when people like make ice cream, so they do like put salt in it to make it colder?
so that it freezes at a colder temperature. It's colder.
So it can hurt your teeth.
That is so cool.
Yeah.
So
So
you
the
can-
reason why they put salt on the sidewalks is because it lowers the freezing point of the ice, making it melt at a much lower temperature, and usually the temperature's above that, and that's why it melts.
Yeah.
Whoa. That is so
Dude, that softball
I
meeting,
love science.
that's some nice ice cream. Yeah, you remember that?
Oh, yeah. What?
Softball meeting last year?
Someone made
That's so random!
Good
Oh my
ice
goodness!
You know the best ice cream is Magnum.
Look at this.
Raspberry. Oh, it's
No.
Look at this!
Okay.
That equation looks
cute.
very familiar. Very familiar! Same thing. Now, so it's F because it's freezing.
What's the D?
What's the D?
Whoa, what?
Wait, what? Oh no, B. There was a
B was boiling, F is freezing. So the equation, you do the equation the exact same way. Now, are you gonna? Would you ever use the boiling point constant in a freezing point problem? No. Okay. But the math done for freezing is exactly the same as the math done for boiling.
What is naphthalene?
Naphthalene.
That's what I'm calling. That's your nickname.
So,
Sounds like you don't know how to say that.
do you still have to think about particle molality?
Yeah.
You have to think about if it's ionic or covalent, if it will break up into more pieces or not. You have to think about that. Okay? But everything else should be done the same. How much will the freezing point of phenyl change if I have 4 moles? That's my solute. Dissolved in 2 kilograms. That's my solvent. So I'm just solving for molality right now. Yeah?
Yeah.
Right? Now, if they don't give you any information that's like, if they don't give you a formula, oh, they didn't tell you it was covalent here. So never mind. So it's covalent, so I do not need to do any particle molality. I don't have to multiply that by anything, right? Okay? Then it wants us to know, what are we solving for here? How much will the freezing point change? So we're solving for solving for this because it wants to change. They gave us KF. Is this any different than the previous problem?
14.8.
Set up the exact same way, same process, same looking equation. Only difference is it's freezing. Now, what is it, 14.8? I do want to make one little subtlety here that's different. It's called freezing point depression, so you would have to subtract that number. Okay? We're done. I realize this was a lot of information. Come in after school if you need help. No, that's, you can say that is the depression. If I ask you for the freezing point, you can subtract it.
And that was like the drag equation.